All right, in these videos, we're going to go over our Unit 5 practice test. This is actually the shortest test that we'll have because there's supposed to be 7 objectives, but I actually combined 4.1 and 4.3 because in my mind they weren't different enough to make like a bunch of questions. So I just combined them because they do something pretty similar. All right, so let's go through this. This is 4.1 and 4.3. 4.1 is the one that's called interpreting the meaning of the derivative in context, and 4.3 is like interpreting the meaning in other contexts or something like that. So they're really similar, so I just put them in one thing. All right, so our first question. All right, the function t equals f of s models the time in hours for a sample of water to evaporate as a function of the size of the sample measured in milliliters. All right, what are the units of f double prime of s? All right, so if I remember f prime of s, too big. F prime of s is the slope of the tangent line, and the slopes have our y values on top of our x values. So for the first derivative, we just put whatever unit is our output on top, whatever unit is the input on the bottom. Now this question is like purposely confusing because so often when we're doing these problems, the time is the input. We put in some time and we get out like a height or a speed or something like that. But in this problem, we're actually putting in this s and we're getting out the t. So it's actually backwards of what you would normally get. So time is actually our output thing. And actually, let's put the actual time that we have. It's hours, because that's the time they tell us up here. And our input unit is measured in milliliters. All right, so that's our derivative units. And then when we do the second derivative, now we're just going to take this unit and do, that's the output of our first derivative, and we do one more of the input unit, so it's another milliliters. So it's going to be hours per milliliter, which our answer is C. And again, it's a bit weird, but again, they're purposely kind of making it weird where the hours is the output rather than the input. All the rest of the questions kind of deal with understanding what the notation means in words. So A of t gives the surface area of an oil slick in square kilometers after t hours. So our input is going to be t, which is hours, and our output is going to be A, which is square kilometers. So A prime of 5 equals 4. The input for the derivative is the same as the input for the original function. This 5 is also going to be a number of hours. So it's 5 hours have elapsed. So right away, that tells me C and D are not right. So it's have to do with 4 hours elapsing. All right, so now the only difference between A and B, now that we know it's 5 hours that have passed, is one has the oil slick growing and one has it shrinking. Everything else about these ones are the same. Well, if the rate is 4, all right, 4 is a positive number, and whenever my rate is positive, that means things are getting bigger. So my final answer is going to be A, right, because 5 hours have passed, the rate is 4, and because 4 is a positive number, it's growing. All right, P of t, or number 3 is really similar. P of t gives the population in billions of people t years after 1950. So again, think about our inputs and outputs. Our input is the time in years, and our output is the population in billions. So P prime, again, the input's going to be the same. So our input is 60, but our thing is years after 1950. So I had to take 1950, and it's 60 years after, which means it's in 2010. So the first thing is this P prime of 60 represents 2010. So immediately I can cross out A and B. And C says the population is that many people, and D says the population is growing by that many people per year. And again, since there's a P prime, that means this number is a rate, a change. So it's not the actual population, it's the change. All right, so it's going to be D is my right answer. All right, so just remember that the prime notation means it's a rate of change, or so something's changing by this amount. It's not actually that amount right now. And then also remember that the input for your derivative is the same as the input for your original. So 60 is also t years after 1950. All right, then the short answers. All right, R of t gives the rate in pints per second. All right, so pints per second is our output, so pints per second of T, that oil is flowing into the tank after T seconds. So T seconds is there. All right, so what does R of 10 equals 3 mean? So first of all, our input is the number of seconds. So after 10 seconds, and then 3 is the original, because it's not R prime, it's just our original R. It's our original output, which is the pints per second that oil is flowing. So after 10 seconds, oil is flowing at 3 pints per second. All right, one thing that makes this question a little confusing is that our original is actually already a rate. It's already per second. So our derivative is going to be the rate of a rate. All right, but this per second is actually our original unit, so that's something that we have to include. And then R prime of 6 equals negative 0.2. Again, the thing in parentheses is our same input, so T seconds, so it's after 6 seconds. And then R prime represents this a rate of change, and it's negative, so it's going to be going down. So after 6 seconds, the rate of oil flow, because that's our original output, is decreasing by 0.2. All right, so it's the rate of the oil flow is our original output, and it's changing by the 0.2. And again, since it was negative to begin with, it's decreasing. And then what of our units? It's pints per second, our original unit, and then per another of our input units. So it's pints per second per second. All right, so 6 is coming from there. This negative tells me it's decreasing. That 0.2 is the rate, and my unit is the original functions unit, and then one more of the inputs unit. So it's pints per second is the original, per second is the new one. All right, so that's how you would do this learning objective. All right, 4.2 is all about straight line motion. So you just have to remember that, all right, we're talking about position, velocity, and acceleration. If you take the derivative of position, you get velocity. If you take the derivative of velocity, you get acceleration. All right, so this one, a particle moves along the x-axis, and we have its position. For what values of t is the particle moving to the right? So if something's moving to the right, its velocity is bigger than 0. All right, so we're going to have to take this equation and figure out when it's bigger than 0. Well, not this equation, because this is the position equation. You take the derivative first. So we get our velocity equation. There's a couple different ways you could do this. You could use the chain rule, or you could FOIL it all out and use the power rule. I'll just use the chain rule. So the chain rule says I'm going to do this exponent first, bring it down 2 times 1/2 is 1, so it's just a minus t. And the derivative of the inside, a is a constant, so even though it's a letter, it's still being represented by a constant, so the derivative of a is 0, and I get negative 1. So that's distribute the negative t minus a. And now we want to figure out, that's our velocity. When is that positive? So we want to do t minus a is greater than 0, which means if I add a to the other side, a is less than t, t is bigger than a, same thing, but that's our answer, B. All right, so just knowing that if I take the derivative of position, I get velocity, and then it's moving to the right if my velocity is positive. Here we have another one, given its position graph. All right, when is the object at rest? All right, it's at rest when its velocity is 0. So we're going to take the derivative of our position graph, again, to get velocity. That's going to be 4 minus 2t. And we're just going to set that equal to 0. Add 2 to t to the other side, divided by 2, and we get 2. And so at time equals 2, it's at rest. A position of a particle is given by that. I would best describe how the particle is moving at t equals 3. All right, so it has moving to the left and right, and speeding up and slowing down in our answers. All right, so moving to the left and right has to do with velocity. So the first thing I'll do is figure out the velocity function, which is, again, taking the derivative, 4t minus 8. And I want to figure out what is the velocity at time equals 3. So now I'm going to plug in 3. And I get 4. That's a positive number, so I know I'm moving to the right. So I can automatically eliminate C and D. How do I determine if it's speeding up or slowing down? I also need to figure out the acceleration. All right, so first let's figure out the acceleration. Take the derivative of velocity, which is just 4. And then I want to plug in 3. There's no t to plug into, so I just get 4. That's also a positive number. And remember, if your velocity and your acceleration have the same sign, they're both positive, then it's speeding up. So my final answer is going to be A, because I know it's not slowing down. If I got -4, then the velocity and acceleration would be different, but they're the same, both positive, so that means I'm speeding up. All right, 8 is basically just a free response of the last question. All right, we have our position graph. When is it slowing down? So the first thing we have to do is find velocity. By taking the derivative, it's going to be t squared plus t minus 12. And finding acceleration, it's going to be 2t plus 1. And then to figure out when it's slowing down, it's all the times the velocity and acceleration don't agree. One's positive and one's negative. All right, so we also need to figure out when is each of these things positive or negative. So we start by setting them equal to 0. All right, this one we can factor. We get t equals 3. We also get t equals -4, but in this problem we only care about positive times, so I can just kind of ignore that one. So t equals 3 is important for velocity. And then acceleration, 2t plus 1, 0, t equals -1/2. All right, so -1/2, again, we can kind of ignore that because it's a negative time. All right, so now the next thing we do is we make these number lines. All right, we're going to start at 0, and 3 is an important time for velocity because that's when we're 0. And for acceleration, there's no important points because the one change in acceleration would happen in negative time that we don't care about. All right, so now we do test points. So we can do 1 here and 4 there. If I plug in 1 into my velocity, I'm going to get 1 plus 1 minus 12. That's a negative number. So I get a negative velocity from 0 to 3 seconds. When I plug in 4, I'm going to get 16 plus 4 is 20, minus 12 is positive. All right, so my velocity is negative from 0 to 3 and positive from 3 on. And my acceleration, I'm going to just do a test point. Let's try to plug in 1. If I plug in 1, I get a positive acceleration. All right, so my final answer, if I'm talking about when something is slowing down, then it's when velocity and acceleration are different. Well, my acceleration is always positive, so my final answer is going to be 0 to 3, right, because that's the time when my velocity is negative, but my acceleration is positive. All right, 4.4 is introduction to related rate. So this is kind of like the first step of related rate problems, and you don't have to solve the whole thing. And then the next learning objective is actually about solving and getting a final answer. All right, so you can read through the problem, but the basic idea is you have this formula, and you want to take the derivative of it to relate the rate. So on the left-hand side, the derivative of u is going to be du dt. On the right-hand side, there's a few different ways you can do it. So the first way is you can do the quotient rule with k over n. Right, k is a constant, so it's just like if it was 2, right, so, or it's pi or something like that. K is just a constant. Another way is to realize that this is kn to the -1 and do the power rule. All right, this is the way I would do it because it's less steps. So if I rewrite it like this, I know this is going to be -k n to the -2. And I took the derivative of an n term, so I get dn over dt. And n to the -2 is over n squared. All right, if you did the power rule, or sorry, the quotient rule, you get the same thing. Just remember that the derivative of k is going to be 0 because k is a constant. All right, but we see which one of our answers matches it, and it looks like it's D. All right, 10. Again, the same thing. We're just going to take our equation and take the derivative of it. But first, we have to make the equation in this case. So x and y are functions of time. The sum of x and twice y is constant. So sum means you're adding of x and twice y equals some constant. And a lot of times we'll use k for a constant. And now we want to relate the derivative. So now we take the derivative. Derivative of x is dx dt. Derivative of 2y is 2. And then I took the derivative of y, so I get a dy dt. And then k is a letter, but it's representing a constant, so its derivative is 0. And then I just have to subtract that to the other side. And you see that exactly matches b. All right, so it's just, this one you just have to do a little bit of work of creating your equation, but then you take your derivative with respect to time. And 11, this one, again, they give you the equation. You just need to take the derivative. The only thing you have to remember about this one that makes it a little bit special is you have x times y, so you have to do the product rule. So I keep my x, the derivative of y is dy dt. And I add, I keep my y, the derivative of x is dx dt, and that equals 0. I remember constants, the derivative of 7 by itself is 0. And I'm solving for dx dt, so I'm going to move this left-hand term to the other side. I subtract. And I want dx dt by itself, so the last thing I'm going to do is divide by y, and that'll give me negative x over y dy dt. So A is my final answer. And again, 12 is basically just the version where you don't have answer choices, but a rectangle is undergoing changes. Find an equation that relates how its perimeter is changing over time. So we need our original equation. Our perimeter of our rectangle is going to be 2 of the length plus 2 of the width. Now we take the derivative. So derivative of p is dp dt. 2l turns into 2, and then dl dt. 2w turns into 2, and then dw dt. All right, that's the whole answer. So you're relating the perimeter to how the other things are changing over time. All right, so that's all I'm expecting for that problem.